Graphs can go down for many different reasons. Here I have 3 graphs that all decrease. This is a standard inverse type of curve. This is a linear curve. And this is something of a hybrid. It looks kind of linear, but it's got some of this curve. What's going on with this one? Well, to understand, let's pull up their mathematical functions. This first graph is inverse, and we're also tacking on this 0.5 power for the x variable. So all of the y values on this graph are being calculated by taking the inverse of the x's and also square rooting the x's. We could write it as an equation like this. The decrease comes from the negative exponent on the x. What about this one? Where is its decrease coming from? Well, it's not coming from a power on the x. The decrease is coming from a negative slope, some negative constant. We knew we would see slope-intercept form because it's a straight line. How about this one? It looks kind of like a straight line, so maybe we expect slope-intercept form. It turns out we are using slope-intercept form, but the x variable has this power. So it's sort of straightish. I mean, after all, the decrease comes from the negative slope. That's important. The decrease here is coming from the negative slope, but it's not straight because of this power. Let's explore this idea a little more before we see how to linearize. Let's say we have a regular linear graph where x is raised to the power of 1, but we have negative slope. If we keep that negative slope, but we change x so that it's raised to the power of, how about 0.5? The graph curves like this. If we change x and add a power of 2 while keeping the negative slope, it curves the other way. So what if we have 0.5 and we want to compare to 0.6 or 0.7? Well, think back. We're going to move from curved and gradually we'll get straighter. So 0.6 might look like this. 0.7 might look like this. And you can see that as we approach the power of 1, the graph gets straighter. Okay, what if we go the other way? Let's start with the power of 2. So we're squaring x. And we get this type of a curve. If we have instead a power of 1.7, what does that look like? Well, it's getting closer to straight. It's less curved. If we have a power of 1.5, or maybe 1.4 for consistency, again, that's getting even straighter, the gray line. How do we linearize this type of a function? Well, remember, we're sort of starting as a comparison. We're starting with y equals slope x plus intercept. And then we're saying, imagine the slope is negative. Next, we tack on this power for the x values. So if your graph looks like this, and your data points kind of gently curve down, not quite straight, not quite inverse, what do you have to do to your data to get a straight line? Well, the typical trick we use is we look at the equation, we figure out what the power is, and then instead of plotting y against all of our x values, we take every x data value, every one of these data points is x value, and we raise it to that power, which is just 0.5. But when we do this, we're not going to get a graph like this, because we have a negative slope and an intercept. So instead, we expect to see our data trace out something like this. It should straighten out. This is how we can linearize a function like I've shown here. We're not going to use a log-log analysis because log-log analyses they kind of get messed up when there's a y-intercept. And so this b, this constant, this intercept, right, where our graph is hitting, that in many ways prohibits a log-log analysis. However, that doesn't mean a log-log analysis isn't useful. If you try a log-log analysis, if your data looks like this, and you try a log-log analysis, and you get something funny, something weird, something that's not straight. Because after all, you know, we look for straight lines. I don't know, something like this, or I'm not sure what it would look like. But the point is, if it's not straight, then that analysis allows you to reject a power function. What's a power function? It's, you know, a straightforward function with something like y equals 4x squared, or y equals 0.5 square root of x, or even if we raise x to a negative power, it could be y equals 6 times 1 over x, or 1 over x to the 2, you know, x to the negative 2 in other words. So all of those are power functions, and you don't have any of them. Nothing like this is the case if you find that your log-log graph isn't straight. That's what log-log graphs do. They test for power functions, and we can tell that, yes, we probably have a power function if the log-log is straight. So it's really valuable still to do this, because it allows you to reject one of the possibilities, and then it opens the door to exploring something like this. Thanks for watching this video.